Hey engineers. So this week we're going to be taking another look at the inputs and outputs on the Arduino. So let's go ahead and jump right in and let's look at the Arduino. So we have so far in Tinkercad explored the digital input-output pins up here, and we've used the power connectors down here to supply 5 volts and connect things to ground. That way we can power things. Um, but there's a whole section that we've been ignoring over here. There's another set of pins with their own set of numbers that we haven't really been touching. So these are called analog input-output pins. And they're similar to the digital I/O pins because they can connect to things, but they do so in a slightly different way and they're used for different things. We're going to be using them today to see how they work exactly. So let's go ahead and start with the difference between digital and analog. So if something is digital, that means that it's in discrete chunks. It can only be very specific values, and it can't be anything in between those values. So digital, because it's always going to be those specific numbers, is usually going to be very reliable and consistent. You pretty much know what you're going to get. And the basic, most introductory version is only going to have 2 possible values. So this is going to be either high or low, or another way of seeing it is 1 or 0, or yet another way, on or off. So that means that there's never going to be a 0.5 if you're looking at something digital. There's never going to be any question if something is on or off. It's either going to be one of those 2 things, nothing in between. In contrast with analog, it still has a maximum and a minimum, but it can take any level in between. So that makes analog measurements and controls good for things that are smooth and continuous, like waves. So digital is going to go straight from maximum to minimum, no in between. You can see how fast that drops. Whereas analog can move smoothly like this. So this diagram right here, this is actually something that would make something like an LED blink. Because if you look at it, it would be going high, low, or LEDs on, LEDs off, on, off, and so on. Whereas again, analog, you can see there's that smooth transition, no vertical drop off like the digital version. So let's look at some examples here. So both the digital and analog pins can be input or output, just depends on the code and the circuit. That's why both of them are labeled I/O. With digital, we're usually going to use it for things that are computer to computer. So the Arduino communicates with a computer in real life with digital signals. Or because it's only going to be those very discrete settings, we use it a lot for on-off switches and things like LEDs where they're either on or they're off, no in between. With analog, since it's a lot smoother, we can look at all those in-between sections. We're going to use it for sensors of all sorts, and also things that are related to sound especially, because sound is, by definition, a wave. The reason we use it for sensors is because real life is usually messy. Unlike an LED or a switch, things usually aren't 100% on or 100% off. We want to be able to measure the in-betweens. So think of something like temperature. Temperature isn't either hot or cold. It's going to be a specific value that's, we need to be very specific about. So let's look at some examples here broken down by digital and analog and whether they're inputs or outputs. So first we've got the inputs. So as we mentioned before, digital inputs are going to be buttons and switches. Again, either on or off. The outputs are going to be turning an LED on and off. There's also some things like motors where they're going to take a digital signal and that's going to tell them to point to a specific thing. On the analog side, we've got an array of sensors. So a potentiometer is like a dial, like picture like a volume dial in a car. A photoresistor is similar to the potentiometer, but it detects light. And then temperature sensors, as I mentioned before. The analog outputs are going to be things that are usually sound related. So something like a buzzer or a speaker. This table is going to be on your assignment today. And it's also going to have a few more options there. Just want to let you know some things are missing from this example because I want you to see, to be able to see the other examples and try and figure out where they need to go. So this table does not have all the answers here for you. Okay, so from here, we're going to go ahead and switch over to the report and we're going to take a look at the Tinkercad. All right, engineers, so now that we know a little bit about the differences between digital and analog connections, we're going to go ahead and actually use them. So from the report, we're going to go ahead and jump into Tinkercad. You guys should have your login info on hand. Now, once we get into Tinkercad, we're going to want to go over here to where it says Learn. And we're going to switch over to Circuits. We're going to go over to Projects. We're going to go all the way down to Show All Arduino. And then we're going to click on Potentiometer. So this is going to give us a basic circuit like this. We've got an LED, it's hooked up to pin 13, digital pin 13. And over here we have this weird looking dial thing. It's connected to power and ground and also to analog A0. This is a potentiometer. This basically acts like a dial. And what it's going to do is it's going to control or act as an input for the LED. Let's start by starting the simulation to see what happens. So it looks like the LED blinks in this setup. And as I move this dial to the right, it starts blinking more slowly. And if I move it to the left, it blinks more quickly, until it hits a certain point where it kind of looks like it stops blinking. So let's go ahead and take a look at the code and see how this actually works. So in the code, we first, so this block right here is going to read the value from the sensor. So it reads analog pin A0 and it saves that to a variable called sensor value. From here, the rest of the code is kind of like the code that we had to blink the LED. It turns the LED on, it waits, turns the LED off, and then waits. Remember, the whole thing is going to loop then. What's different about this though, is that the duration of the wait, the amount of time that it's waiting before turning the LED on and off, that's based on this sensor value. So what that tells us is that in our potentiometer here, as we move it to the right and that slows down the blinking, that tells us that this is going to a larger value. And as we move to the left, that tells us that we're going to a smaller value. Because remember, a shorter delay is going to be a faster blink. Now, the really cool thing that we can see here is that it doesn't really matter how small of an adjustment I make. We can see the reaction change here. If this was a digital input, we would only have a certain number of inputs that we could have. For example, if we had a switch, it could only be on or off. If we had a button, it's only on or off. But with this, we get this smooth control as opposed to the very jerky control of the other one. All right, engineers, so this basic setup, this is going to be one part of your assignment, but I want to take this one step further. I want to actually make some changes to this. I'm going to start by making changes to the circuit. Our LED is doing great connected to pin 13, but I want to move it to a very special pin. I want to move it over to pin 11. You can see that pin 11, unlike pins 13 and 12, has this little tilde next to it. That's going to help us out, but we're going to have to keep going and take a look at the code to see exactly why. So let's jump back over to the code, and from here, I want to get rid of almost everything here. The only things that we're going to keep are this sensor value bubble right here. We can pull this out and keep it aside, and this set sensor value block at the top. Everything else down here, toss it in the trash. So we have the LED right here on pin 11, and I want to be able to set the value of pin 11. But I don't want this block here, because I don't want to just be able to set it to high and low. Instead, I want this one right here that has a number here. So let's drag this out. When we click on this drop down, we can see that there's only certain pins that we're allowed to set it to. There's 3, 5, 6, 9, 10, and 11. We do have our LED on pin 11, and one thing that all of those pins have in common is they all have that same symbol. We're going to take a closer look at this in just a minute after we see what this program does. We're going to be setting pin 11 to the sensor value. That's what we're going to plug in right there. And just to have a little bit of control here, I want to have a wait block in here as well. I'm going to have this wait be very, very short. I'm going to leave it at 50 milliseconds. So let's go ahead and see what exactly this does. So the LED is on. It's no longer blinking. And as I move this dial, you can see what the LED does. If I move it to the far left, it turns off. And as I move it to the right, it starts to get brighter. Now there's a few, I'd say, bugs in Tinkercad. You can see there's kind of points in here where it gets brighter and dimmer again. But I think the important part is all the way to the right, where we're measuring a bigger number, the LED gets its brightest, and all the way to the left, the LED gets its dimmest. So what we've basically done here is we made a dimmer switch for the LED. We're not controlling the blinking, we're controlling the brightness now. Now, as for why we can only do this on specific pins, well, that has to do with the way the LEDs work. So let's go ahead and take a look at what's so special about these pins here. Alright, so you might be wondering why we needed to switch the pin for the LED from 13 to 11. Well, the reason is because pin 11 is a special pin that's capable of something called PWM. And that's because LEDs are digital devices. So they want to either be on or off, and we can't dim them. We can't go to an in-between state just by reducing power. But they are incredibly fast to respond. So we can use some tricks to get to the same place. And that's where PWM enters. So PWM stands for pulse width modulation. What it does is turns the LED on very quickly so that it looks like it's not quite as bright. So here is a diagram that explains what PWM does. So down here at the bottom, we've got what's called 100% duty cycle. That means that the LED is just on the entire time. And what PWM does is when we want to dim the LED, we don't just take this line right here and bring it down, because the LED doesn't like being down here in this in-between state. Instead, we flick the LED on and off so quickly that, for example, here at 75% duty cycle, the LED is only on 75% of the time, and it happens so fast that your eyes just kind of blur it out, and we go into this in-between state right here. And we can use this to get down to much lower duty cycles. Once you get down really low, the LED is off for so long that it starts to look kind of flickery. So it's not perfect, but this is a good trick to kind of give us some more functionality for LEDs. An interesting side effect of this is with newer cars, they often have LED headlights. So if you ever take a video or see a video of a car driving around, a lot of times you'll see the LEDs look like they're flashing like crazy. And they don't look like that in real life. That's because the cameras are picking up the PWM that's dimming the lights, especially during the day. And that's something that your eyes aren't seeing. Alright, so PWM, it's basically a trick to get a digital thing to act like an analog thing. It's just a neat trick of electronics, and that's why we have to use that other specific pin, and that's how we can dim the LED. Alright, engineers, so that's the last bit of information here. So you guys can take all of this and use it to fill out your report. I hope you guys had a good time with this lesson this week.